Good morning, everybody. Welcome to Chem 1211 with your host, me, Dr. White. And hopefully you're ready for an exciting morning. We're going to do some fun chemistry and then have a really exciting lab. So I hope you're all fired up. All right, today I promised I'd go through Chapter 9, problem sets 1 and 2, and Dr. White keeps his promise. And don't forget, don't fall behind. Do the problem sets. They help you do well. All right. But before I start, let me remind you something important. Don't forget, in my class, in my universe, there's no such thing as a dumb question. Always feel free to ask questions. And don't forget, on Monday and Wednesday nights, I have my office hour on Zoom. And if you need extra help, let me know. I can sneak you in somewhere when I'm free. All right. I'm going to ask my thumbs up people because Zoom's been sometimes iffy for me. See the practice problem, part 1? Okay. Now, let's look at this. 3 points each. If you were to see it sometime in the future, and the question is, write the electron configuration for nitrogen. Well, what does that mean? That means you're going to show all. And again, electron configuration is for all electrons. So you have to know how many electrons nitrogen has. And you go to the periodic table and you find the atomic number of nitrogen is 7. Therefore, it has 7 electrons. Now, if we were in class, in a classroom, I would do the following, but I'm going to do it here on Zoom. You should know for electron configuration, hold on one second. My little screen was in the way. This will be given to you on test number 2. We look at a shell. The names are 1, 2, 3, and 4, very tough. And the number of subshells, shell 1 has 1, 2 has 2, 3 has 3, and guess what? 4 has 4. Now, when we look at subshells, having a bad writing day. We have a subshell. There are actually 4 of them. S, P, D, and F. That's the D. 2, 6, 10, and 14. Now, little secret. Remember my gift. You only have to know how to do the elements up to 12. Therefore, you don't have to worry about D and F. I'll say it again. Our secret. Remember, what happens on Zoom stays in Zoom. Oh, that was awful. But anyways, remember, you only have to know S and P. And I'll give you that tables, but just to remind you, So how do you do that? Remember, and this you have to remember, you always fill from the lowest to the top highest. So you always start with 1, 2, and then 3. Same thing here. You always start with the lowest subshell of any shell. Therefore, you always start with S and then go to P, and you can't tell what that is, so I'll rewrite it again, go to D and F. So if we look at here, we have 7 electrons. What's the first shell? 1. How many subshells does it have? 2. What am I saying? 1. I'm getting ahead of myself. And how many electrons can you put in S? 1s, 2. Remember, a subshell is both a number and a letter. A subshell is both a number and a letter. So 1s subshell, I put in my 2 electrons. Next, I'm going to go to a different color. I only have how many subshells in 1? And the answer is 1. Therefore, I have to go to the next shell, which is 2, which has 2 subshells. The first subshell in 2 is 2s. How many electrons can I put in any s orbital? 2. I do. Well, 2 plus 2 is 4. I got to get to 7 because we're looking at the total number of electrons. And therefore, guess what? I go to the second subshell because shell 2 has 2 subshells, and the second one is 2p. Remember, a subshell is a number and a letter. And I'm on the wrong one, number and a letter. And therefore, 2 plus 2 is 4, 7 minus 4 is 3. I'm done. Now let's move down to magnesium. And again, the same question. Draw the electron configuration for magnesium. What do you have to do? First of all, electron configuration is all the electrons. And if I notice, I made a mistake there. All right, so we have 12 electrons. And the first shell is 1, and it has 1 subshell, and that's 1s, and I put my 2 electrons. Well, 1 only has 1 subshell. Well, I filled it. Now I have to go to the next shell, which is the next lowest energy, which is 2. And 2 has 2 subshells. The first one is 2s, and I'll put in 2 electrons because that's all I can put in any s subshell. Well, 4, I got a lot more to go. The next subshell in 2 is 2p because you go down. And how many electrons max can I put in 2p? 6. Well, I'm going to put 6 in. So 2 plus 2 plus 6 is 10. I have 2 left to go. I'll put it there because the number fell off, and I'll put it back in. How many electrons can I put into S? Any S? 2. This is shell 3 because 2, I only have 2 subshells, and that's why I had to go to 3. Let's do it again. I filled in 2p, and shell 2 only has 2 subshells. Well, I've used them. And now I have to go to the next shell, which is S. The first subshell, next shell is 3. Boy, I'm off my game today. Hold on, I got to reboot. I've rebooted. Next shell is 3. And the first subshell in 3 in any shell is always S, and you call that 3S, and I can put in 2 electrons max, and that's what I have. And that's how you do that. Now, another important area that we talked about in this chapter are the valence electrons, and you should know being subtle today. Hint, you should know what is a valence electron. The valence electron, that's the outermost electron or electrons of an atom. How do you find valence electrons? Well, you look at your periodic table. Hang in there, I got to open up a periodic table, which I didn't do. Hang on while I'm finding it. Oh, come on, was my computer slow? There we go. And everybody see the periodic table? I see somebody already beat me to it, saying thumbs up. Thank you. Now, the number at the top, either Roman numeral, if you notice I have in red, and also smaller in black, and I made it larger in red, those are the number of valence electrons. If we look at lithium or hydrogen, they have 1. Magnesium, calcium, 2. Go all the way over here, fluorine, chlorine, bromine, iodine, 7, helium, neon, argon, krypton, xenon, the noble gases, 8, and carbon, my favorite, 4. So let's go back to the problem set, because it asks you how many valence electrons do the following elements have. Well, you look at the top, I just showed you hydrogen has 1, carbon, the number at the top of the column for carbon is 4, and oxygen is 6. Iodine, which is a halogen, I showed you 7, and krypton, which is in our universe, is a colorless gas, not a green solid that kills Superman, and that's 8. I always enjoy when you see one of the Superman movies with Krypton or the old comic books where, oh, look, it's a green salad. No, it isn't. I guess, oh, warning, awful joke time. If Superman comes from Krypton, does that make Krypton a noble planet? So I said it was an awful joke. You can go, All right, any questions on electron configuration or noble, I got my head fixed on noble, but anyways, on valence electrons, any questions? I actually should look at the chat down here. Going once, twice, let's move on then. Remember, you can always ask questions in my class, they're encouraged. And as one student told me, you allow questions and you even answer them. All right, let's look at the next problem set, same chapter. I split it up into two different ones. Can everybody see part 2 on their screen? Thumbs up, people. Can you see part 2 on your screen? Okay. All right. Now we're dealing with covalent bonds. And covalent bonds are sharing pairs of electrons. And the first thing I asked you to do is Lewis structure. Whenever you see the term or the words Lewis structure, we're talking about valence electrons. So how do you draw the Lewis structure for water? Well, it's simple. You say hydrogen has one valence electron, oxygen has 6 valence electrons, and hydrogen, the second one, has 1. And a better way to draw it is like this. This electron on hydrogen looks at this single electron oxygen and says, ooh, let's share. Because sharing a covalent bond is when we share pairs of electrons. And it does. And then the other one does the same thing, and it does. So if you want to impress your friends, family, and loved ones this weekend, you see them drinking water, you can say, do you know water has 2 covalent bonds in it? Now, if we come down here to, let's look at hydrogen cyanide. And here we have hydrogen with 1 valence electron, carbon with 4, remember Lewis structure, 1 dot on each side, and nitrogen with 5, you put 1 on each side before you double up. And this hydrogen says to the carbon, oh, you got an electron? I've got an electron, let's share. And they do. Now, carbon has 3 unpaired electrons left over, looks over at nitrogen, which has 3 unpaired electrons, and say, you've got 3, I've got 3, let's share. And they do. And the non-bonding electrons are still there. Now, if I lose you, it went away. It said my internet connection was unstable. Help. Now, remember, when we talk about chemical bonds, covalent bonds, there are 3 types that you should know. And if we were in class, I'd be writing this on the whiteboard and you'd be taking notes. But good news, you can watch the video. And if we have the 3 covalent bonds, single bond, 1 pair of electrons being shared, double bond, 2 pairs of electrons being shared, triple bond, 3 pairs of electrons being shared. Again, you should know. Ooh, I better be subtle again. You should know, hint, you should know this. What are the 3 types of covalent bonds? Single bond, double bond, triple bond. You should also know how many pair of electrons in each one. Single bond, 1 pair, double bond, 2 pair, triple bond, 3 pair. Now, in C, HCN, hydrogen cyanide, I'm going to give you I'll hold 22.5 seconds. What type of covalent bonds are in HCN? It feels like 22 seconds. I'll give you another 5 in case I counted wrong. 1, 2, 4, 5. Done. All right. Now, if we look over here, between the carbon and hydrogen, 2 dots, what does that tell you? 1 pair of electrons. Remember, a pair means 2, and that's a single bond. If we look between the carbon and nitrogen, you see 6 electrons, 3 pairs, and 3 pairs is a triple bond. So in HCN, hydrogen cyanide, there's a single bond and a triple bond. Now, let's look at the next one. And if we look at sodium hydroxide, whenever you see an alkali metal, that always forms a cation. The alkali metals always give up 1 electron, they're 1 valence electron, to form a +1 charge. So if we look at this, we have sodium, which will form a +1 charge, oxygen with 6 valence electrons. Go to your periodic table, look at the top, hydrogen with 1 valence electron. So I have my sodium, and let me rewrite it here. My oxygen has 6 valence electrons. Hydrogen has 1. Hydrogen says to oxygen, I have 1, you have 1, let's share. And it has. Remember, the driving force, except for hydrogen, which octet is 2, all atoms try to get 8 valence electrons. Well, if you look over here, hydrogen has 2, but oxygen has 7. Oh no, that's not right. Well, it actually has 8, because the electron from the sodium to make the sodium cation goes to the oxygen, and now you form the hydroxide anion, and now sodium hydroxide has both a ionic bond between the sodium and the hydroxide polyatomic ion, and a single bond between the oxygen and hydrogen. Boy, that's pretty complex. Now, I'll skip the number 3. I've already done this, but what are the 3 types of covalent bonds, and how many pairs of electrons are in each type of, and it should be the bond. Oh, it must have fallen off. Anyways, single bond, 1 pair of electrons, double bond, 2 pair, triple bond, 3. Next, give an example of a molecule that can hydrogen bond, and hydrogen bond means its examples are oxygen, nitrogen, or fluorine with a hydrogen atom on them. And the most popular and most widely used chemical that can hydrogen bond is water. Ammonia can, all alcohols can, and hydrogen fluoride, HF, can. And there we are. Now on Tuesday, I'm going to have to look up, I forgot what's the problem set for ionic bonding, but we'll go through that. All right, any questions on what I just did with covalent bonds? Practice them. You should practice that. And I'll put out an email, I forgot what chapter it is, with ionic bonds, and we'll do that on Tuesday. Make sure you keep up, because I might as well tell you the truth right now, and that is test number 1 is always the highest average of the semester. Test number 2, not always, but a lot, is the lowest average test of the semester. Why am I telling you that? So you keep up. Like last semester, they listened to me, and it wasn't the lowest. They did quite well. And I hope you all do quite well. How do you do that? Keep up with the practice problems. Well, done with that commercial. Let's move on. But truthfully, it is important. And test number 2 is probably the most challenging of the whole semester. But if you do the practice problems, you do well. All right, everybody see chapter 6 on the screen? Thumbs up, people. Thank you. If anybody knows anybody senior at Zoom, send me an email with their name and phone number so I can tell them how to fix their problems. All right. On Tuesday, I started talking about the mole. The mole is the counting unit used by chemists. And it's the unit, one way of defining it is 1 mole is 6.02 times 10 to the 23rd, and that's called Avogadro's number. Now, I taught you on Tuesday that when you have A equal B, you can have 2 ratios, A over B and B over A. Therefore, if 1 mole of something equals Avogadro's number of whatever, remember, by the way, there's still plenty of time. I told you about my favorite birthday gift. All I want is a mole of pennies. And that's 100 million piles, and each pile has $1 billion. It's just a mole, and it's just pennies. So start saving now. All right. Now, once you know this, you can write 2 ratios. You don't have to memorize this, but you should be familiar with this. Now, in chemistry, what are the things we count? Atoms and molecules. And therefore, 1 mole of an element is Avogadro's number of atoms of that element. 1 mole of a compound equals Avogadro's number of molecules of that compound. And you can have the 2 ratios, Avogadro's number of atoms or molecules per mole, or 1 mole per Avogadro's number of atoms or molecules. And on Tuesday, I started teaching you, and it's time again, do some practice with your good buddy, your good friend, unit analysis. And truthfully, it is this semester going to help you through all the math. We're going to have to relax. I'll teach you how to do it. Take a deep breath, relax. Oh no, where did my whiteboard go? Hang in there. All right, let's take a look at the following. And the question is, and I'll decode it, how many atoms, gold, AU is gold, are 5.374 moles of gold? So you look at that and say, what do I do? Well, the first thing you do is figure out what are you being asked to find? Atoms of gold. So I like to put a question mark. That's an awful looking question mark. That's better. We're trying to find atoms of gold. What are we given? Well, I have 5.374 moles of gold. And now we're going to use our good buddy, our good friend, unit analysis. Remember, I'm going for the Guinness Book of World Records saying that the most times in a semester. And what do we have to start with? This number, 5.374 moles of gold. What am I trying to get to? And I'll put equal and the units, atoms of gold. Now, if you had a magic ratio, it's not magic, it's chemistry, that you could multiply moles of gold to get the atoms of gold, what would that ratio be? Well, here's where you use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of that ratio. Whatever units you're trying to get rid of go underneath. And now I'm going to put those units there. Atoms of gold on top and moles of gold underneath. And where do we get that information? And this will be given to you. 1 mole of an element equals Avogadro's number, 6.02 times 10 to the 23rd atoms of that element. Therefore, I can put on top, remember, A equals B, two ratios, A over B or B over A. I can put on top atoms of gold. I'll put Avogadro's number, 6.02 times 10 to the 23rd. And underneath, I know 1 mole equals Avogadro's. Now, remember, 1 is an exact number. Avogadro's number is the actual calculated number, and the value I use and always have, most chemists, is 3 significant figures. One time, a couple of years ago, I had some time to kill, and I found a reputable website that had Avogadro's number to 18 significant figures. Who needs that? I don't know, but whoever did, someone calculated it for them, or that person needed it for themselves. I don't use that. Now, before you pick up your calculator, it's time to use your good buddy, your good friend, unit analysis, and you say, do I get the right units? And let me remind you, anything divided by itself equals the number 1, which means it's canceled out. And notice here we have moles of AU gold divided by moles of AU gold. That cancels out. What do we have left? Atoms of gold. We're gonna go, we're on the right track. And now I can pick up my calculator. Let me get my spreadsheet open. Make it nice and large for you. And so I have 5.374 times Avogadro's number, 6.02 times 10 to the 23rd. And Let's see if I'm in screen sharing mode with the right screen. I am. And everybody should see the spreadsheet. And this is the number your calculator gave you. Now, 5.374.
Dr. White, we can't see we can't see the spreadsheet, Dr. White.
Zoom tells me you
Thank you.
should. Do you see it now? That's why I asked for my thumbs up, people, because it burps on me like that. Worse than burp. But anyways, now that you can see it, 5.374 is 4 significant figures, but Avogadro's number is 3 significant. So I'm going to let you try first, then I'll do it. Round that off to 3 significant figures. Time's up. Keep the 3, keep the 2, keep the 3. We use the 5 to round off. Is that 4 or less or 5 or higher? Time's up. Hopefully you pick 5 or higher. I'm going to drop that and all the numbers after that before the E, which is 10 to the power 24, and increase the 3 to 4. So that'd be 3.24 times 10 to the 24th. And that's how you do that. And because I'm such a nice guy, I'm going to share too. I'll let you have some fun. And the question is, how many molecules of HCl, and you'll learn later in the semester, that's hydrochloric acid, are in 9.47 moles of HCl? Go. Remember, find out what are you trying to be, what are you being asked to find, and what are you given, and then use your good buddy, your good friend, unit analysis. Psst, you're doing high-level chemistry. You are? If you're having a little difficulty with this, I'll do this. Don't forget, you're just starting out. And remember, 1 mole of an element or a compound equals Avogadro's number of either for an element atoms, for a compound molecules. If you don't have your calculator, just set it up. Don't forget to use your good buddy, your good friend, unit analysis. And when you're done, give me a thumbs up. All right, let's take a look at this. And the problem is how many molecules of HCl are in 9.74 moles of HCl. So what are we trying to find? Molecules of HCl. What are we given? This number, how many moles of HCl? And how do we proceed? We use our good buddy, our good friend, unit analysis. This is the only number I have to start with. So I will. And what answer do I want unit-wise? Well, I figured that out. Molecules of HCl. Now, if I had a magic ratio, no, it's not magic, it's chemistry, what would I use in that ratio? Well, now you use your good buddy, your good friend, unit analysis, and whatever you're trying to get to, the units go on top of that ratio. Whatever you're trying to get rid of, the units go underneath. And what I mean by get rid of, you don't want the moles of HCl in your final answer. You want molecules. Now, I want molecules HCl on top, and I want moles HCl underneath. And where do I get that number? And you'll be given this on test number 2, but you should know how to use it. 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of the compound. In this case, it's HCl. So over here, for moles, I can put in 1 from 1 mole equals. And for molecules of HCl, on top of the ratio, I'll put 6.02 times 10 to the 23rd. Now, before I pick up my pen, my calculator, I'll look at using unit analysis. Remember, anything A divided by A equals the number 1. It cancels out. And here I'll have moles of HCl divided by moles of HCl. So this cancels out, and I'm just left with molecules of HCl, which is what I'm trying to go to. So I will get the correct answer, hopefully. And now it's time for me to go to my calculator. Everybody see the spreadsheet? That's empty, good. All right. 9.74 times Avogadro's number, 6.02 E 23. Oh, look at that number. Now, 9.74 was 3 significant figures, and Avogadro's number, 6.02 times 10 to the 23rd, 602, is 3. I'll let you round that off to 3 significant figures. Go. Time's up. keep the 5, keep the 8, keep the 6, use the 3 to round off. Is that 4 or less? Yes. So I drop the 4 and every 3 and everything afterward and keep the 10 to the 24th. So the answer would be 5.86 times 10 to the 24th. And that's how you do it. Now, some words to help you out on to the wise on test number 2. Show your work like this. What happens if instead of on your calculator, you put in 9.47? You're going to get the wrong answer. If you just put down a number here, nothing else, and it's wrong, I'll give you 0 points. If you were to show your work like I have right here, and you put down the wrong answer because you punched it in wrong in your calculator, on a 5 or 6 point problem, I'll only take off 1 point because it's a math error. So it always pays to show your work. And that's how you do that. Now, if I look at the clock, we got about 2 minutes left. I'm going to give you a special Thursday break. Let's take an extra long break because it doesn't make sense for me to rush and try and finish a problem in 2 minutes because that doesn't help you. So don't tell anybody I'm being nice. I'll see you at 10:55 because Dr. White's going to stretch because I've been sitting almost an hour and my legs say time to stretch. I'll see you in 6 minutes or so at 10:55. Come back. Hi, Murray. I saw your question, and the answer is no. And the next one, I'll be showing you why.
I just noticed because when we were doing both problems, we were looking for different things, but you put the one as the denominator.
It was actually the same thing.
Oh,
From
okay.
moles to either atoms or molecules. And now we're going to do something different when everybody
Okay.
comes back.
Okay, great.
I keep on seeing your shelf behind you, and I have the same one in my utility room.
I
And
love it.
I love it, but it was a pain putting it together alone.
I know, me too. Unfortunately, mine is getting a little bit too cluttered right now.
Actually, mine has about 3 times as much stuff because I don't have utensils. It's my pantry I use. And with COVID-19, especially when it first kicked off and it was really what's going on, I stocked up and said, I'm going to try and buy as much non-perishables as I can.
That's a good idea.
I don't have to go out that often.
True.
And I went hog wild in Costco and my local supermarket, Valley. I went,
Well, and with the winter season coming up, you may have to do the same, you know, or hopefully that stuff has lasted.
well, you got things like dry goods, navy beans and stuff like that.
Right,
And
right.
plus I have a monster, I have a freezer that's almost as big as your shelving unit. That's stocked up too. So I could probably, and my parents had one like that. I wonder where I learned that. Me and my sister all went out and got them when we got our own place. And it's time to start again. Now, one of your colleagues asked, is one always at the bottom of the denominator? Well, in case you forgot, and I still remember, even though I went to Michigan State and I don't like the school, but Notre Dame, ND, numerator, denominator. But anyways, let's get to work. Now, if you notice up here, you're trying to find how many molecules are the one before atoms. Let's do another one. Oop, wrong color. Right color. And let's take a look at this. I'll decode it in case you haven't figured out my scribbling. And that's how many moles of Br2, bromine gas. I'll teach, we already saw that, but bromine gas exists as Br2, are in 7.11 times 10 to the 26 molecules of bromine. So first thing you do is, what are you being asked to find? Moles of bromine. What are you given? 7.11 times 10 to the 26 molecules of bromine. And how do you proceed? Well, there's only one number we have, 7.11 times 10 to the 26 molecules of bromine. And if there was a magic ratio, no, it's really chemistry. What units do I want to get to? Moles of bromine. And now it's time to use you. I'm going to do it. Your good buddy, your good friend. Unit analysis. And how do you use that? Whatever you're trying to get to unit-wise goes on top of that ratio. Whatever you're trying to get rid of goes underneath. And now I'll draw those, write those in. On top, I want moles of bromine. Underneath, I want molecules of bromine. And where do I get those numbers? 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of that compound. And in the past, I used to make students memorize this. 2 years ago, I've decided which is more important, you showing me you know how to use this stuff or how good is your memory. And I decided you show me how you know how to use this, not just also me testing your memory. So remember, if you have A equal B, you have 2 ratios. And if we come up here, what do we put in moles of bromine? 1. Because 1 mole of a compound, bromine, equals what? And the bottom, 6.02 times 10 to the 23rd. And before I pick up my calculator, I will check. Notice I have moles of bromine divided, or molecules of bromine divided by molecules of bromine. Anything divided by itself, A divided by A, equals 1, cancels out. That cancels out. I'm left with moles of bromine. Hey, that's what I want for my answer. So now I can pick up my calculator. And go to my spreadsheet. Everybody see the spreadsheet? I assume you can. Everybody, thank you. All right. And now I'll take and do, I want 7.11 times 10 to the 26th divided by Avogadro's number, 6.02 times 10 to the 23rd. And I get this number. Now, 7.11, 3 significant figures. 6.02 times 10 to the 23rd, 3 significant. How many significant figures should your answer be? 3. Keep the 1. Keep the 1. Keep the 8. Use the 1 to round off. Is that 4 or less or 5 or higher? And time's up. Less than 4. So I'm going to drop that and everything afterward. Keep the E 10 to the 3rd. And the answer here will be 1.18 times 10 to the 3rd. And like test number 1 and test number 2, it will say underneath your name, please use proper significant figures for all calculated answers. And that's how you do this type. And notice 1 is not always at the bottom. Now, I know some instructors say for this type of thing, you got to memorize this ratio. For this one, you got to memorize this. No, use your good buddy, your good friend to show you what goes underneath, what goes on top. And it's time for Dr. White to share the fun. And now it's your turn. And for our test, this might be 5, 6, or if I was in a good mood, 7 or 8, who knows, but at least 5 or 6 points. How many moles sodium fluoride NaF is sodium fluoride. That's in your toothpaste to keep your teeth healthy and your gums too. I think it's more for your teeth. Are in 8.97 times 10 to the 23rd molecules of sodium fluoride. Your turn. Go. If you don't have a calculator, just try setting it up. And when you're done, give me a thumbs up. And for those who are quicker than others, please be patient. I try and give everybody time to finish. See what a nice guy I am? If I say that enough times, you might believe me too. Just think, you have to pay to put up with all this bad humor. All right, I think, is everybody done? Give me a thumbs up if you're done. Well, all right, I think everybody's done. I'll give you another 12.2 seconds. 10, 12, 12.2, time's up. Let's do it. All right, first thing you do, you read the problem and you figure out, what am I trying to find? And the answer is moles of sodium fluoride. What am I given? And the answer is 8.97 times 10 to the 32nd molecules sodium fluoride. So what do I have to start with? This number, 8.97, that's the only number I have to start with, times 10 to the 32nd power of, that's a big number, molecules sodium fluoride, NaF. And if I had a ratio, I could multiply it by what units do I want my final answer to be in? Well, you already figured that out by the question mark. Moles of sodium fluoride. And now it's time to use your good buddy, your good friend. I'm not going to use the whistle. I don't want to overuse it, but it is time to use it. Whatever I'm trying to get rid of goes underneath the ratio. Whatever I'm trying to get to goes on top. And we're talking about the units. And now I know what goes on top and bottom. Unit-wise, I can write on top moles, NaF, underneath molecules, sodium fluoride, NaF. Where do I get that number? And you'll be given this at the end of test number 2 under important information. And that is 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of the compound. And therefore, you know, if A equals B, they're two ratios. So if I look up here, what do I put for moles of sodium fluoride? The number 1 from this ratio, or this definition. Remember, 1 is an exact number and doesn't play a role in significant figures. What do I put on the bottom? Avogadro's number, 6.02 times 10 to the 23rd. Now, before I pick up my calculator, I'm going to look at my units. Notice I have molecules, sodium fluoride divided by molecules. That cancels out. I'm left with the right units, so I can pick up my calculator. Now, before I do this, let me show you how unit analysis is your good friend. What if I set this up backwards or upside down? And this is wrong. The reason I'm showing you this is because students do this. And if you look at this, what's the units of my final answer? This molecules of sodium fluoride divided by moles of sodium fluoride won't cancel out. So I'm left with molecules sodium fluoride times molecules sodium fluoride divided by moles of sodium fluoride. I don't want that. So what that tells you, when you get this kind of wrong units, this is wrong. You made a mistake, and you've got to look at this ratio again. And that's why I take the time to see if my units cancel out. And they did, the one I did correctly. And so it's time for me to go to my calculator, because now I know I've done it right. .97 times 10 to the 32nd power divided by 6.02 times 10 to the 23rd. Ta-da! And we get this number. And how do I round this off to 3 significant figures? Because Dr. Whiteson has read of 3 significant figures. And here we have a 1, a 4, a 9. Those are my 3. The round off number is 0. Is that 4 or less or 5 or higher? And hopefully I'll pick 4 or less. So that's 0, and everything afterward before the 10 to the power I drop. So the answer here would be 1.49 times 10 to the 9th. .49 times 10 to the 9th moles, that's the 9 moles of sodium fluoride. And that's how you do it. So let's go through what was important here. You look at a problem, figure out what are you being asked to find the units. Next, what are you given? And then whatever you're given, you start with, you look at what units you're trying to get to. You think about, if I can convert what I'm starting with to the units of my answer, if I can do that by multiplying by a ratio, use unit analysis, your good buddy, your good friend. What goes on top of that ratio is what you're trying to get to. what goes underneath is what you're trying to get rid of. Then where do you find something equals something else to put in that ratio? Here in this case, 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules. You put the numbers in, check your units, do the math, and you're done. So we've done our practice with, and it's practice time number 1 or more, using your good buddy, your good friend, unit analysis. Let's move on. Now this part, subscript states of moles of elements, I'm going to skip. I should have taken it out. All right. Now we're coming to one of the most important concepts in all of chemistry, general chemistry, dealing with moles. I see some questions. Hold on. All right. The question is, can you review how we get 10 to the power answer? Is that how I did it or how you do it on a calculator? All right. Just so happens I have my calculator. Don't forget, when it's on, make sure when you're doing it, after class today, I'll spend a couple minutes, whoever asked how to do that, but make sure when you're doing it, if you have this kind of calculator, all right, what you probably to get that is you didn't divide, you multiplied. I'll bet you that's what you did. Remember, this is division and this is multiplication. And good news is, what if you did that on a test? If you show your work, I'd say, oh, math error, 1 point. If you didn't show your work, 0 points, 0. So it's always good, 0, to show your work so you don't get 0. If you have problems with your calculator, see me after class. All right, looks like you resolved that. Good. Remember, there's no such thing as a dumb question in my class ever. All right, now we're going to talk about what's called molar mass. And what molar mass is, and this is very important, for an element, the quantity in grams of that element equals the atomic mass of that. And for a molecular molar mass, the quantity in grams for the formula or molecular weight of a molecule equals the formula mass of that. And what that really means is 1 mole of an element equals the atomic mass in grams. So if we look at gold, let's take a look. Do I still have my periodic table? I closed it. Let me open it again. All right, everybody see the periodic table? All right, good. Now, 1 mole of an element equals its atomic weight in grams. Therefore, what does 1 mole of gold, AU, equal in grams? The 3 significant figures, 197. What does 1 mole of copper equal? The 3 significant figures, 63.5 grams. And that's an important concept. 1 mole of an element equals its atomic mass in grams. Also, you can use other units, but for this class, I will stick to grams. What that also means is 1 mole of a compound equals the molecular weight also sometimes called formula mass. I like molecular weight myself, and that's what I'll use, in grams. So 1 mole of a compound element equals its atomic weight in grams. 1 mole of a compound equals its molecular weight in grams. And you learned earlier, the molecular weight was the sum of all atomic weights. These will be given to you in test number 2, but you got to know how to use it. Now, one of the things that normally happens at this point is a student goes like this. I'm confused. You told me, Dr. White, 1 mole of a compound equals Avogadro's number. Well, how can 1 mole of a compound equal its molecular weight? Because what's going on? Well, think of it this way. If you think about a dozen, if you have a dozen feathers, how many do you have? 12. If you have a dozen, I don't know, let's pick something heavy, cannonballs, made out of lead, how many do you have? 12. Do they have the same weight? No. If you had 12 feathers that are always identical, you could weigh them and you get a weight. I don't know, 120 grams. You have 12 cannonballs and you weigh them, you get a much bigger weight because they're heavier. I don't know how many kilograms that would be, but a lot. But if they're always identical, 12 cannonballs would always be that weight, and 12 feathers would always be that weight. But you'd always have 12. Well, the same thing with atoms and molecules and compounds and elements. 1 mole of an element or compound, Avogadro's number, but 1 mole in terms of weight for an element, the atomic weight, for a molecule or a compound, the molecular weight. Let's see how to use this. Everybody see my whiteboard? Thumbs up, people, help. Everybody see it? Thank you. And let's look at the following 6 or 8 points, depending on my mood, maybe even 10. How many moles water are 37.1 grams of water? What do I do? Well, find out what units you're being asked to find. And that's moles of water. Next, what are you given? 37.1 grams of water. What did I do? Well, I only have one number, and therefore I'm going to come over here and start here. 37.1 grams of water. And it's time to use your good buddy, your good friend, unit analysis. If I had a ratio I could multiply grams of water by to get to my answer, what units do I want my answer? Moles of water. And now I know how to use unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. So on top, I want moles of water. Underneath, I want grams of water. And the question is, where do I get that? Well, 1 mole of a compound equals its molecular weight, and I'm going to abbreviate by MW, molecular weight, in grams. Uh-oh, Dr. White didn't give us the molecular weight of water. No, you got to calculate that. How do you do that? That's the sum of all atomic weights. And the molecular weight of water, you have 2 hydrogen, 1 oxygen, and the atomic weight of hydrogen to 3 significant figures is 1.01. Oxygen, they're one of them, 16.0. Do the math, 2.02, and 1 times 16.0. Add these up. Remember, when you add, you get the same number of significant figures past the decimal as the number that has the fewest. This is 1, this is 2, 1 is the lowest, keep the 0. Use 2 to round off. Is that 4 or less? Yes, I drop it. So the molecular weight of water, which we did before, is 18.1. And from 1 mole of a compound, let's call it water, so I can put that up there, is how many grams? 18.0. And now, before I pick up my calculator, I'll check and see, did the units cancel out? And if I look over here, grams of water divided by grams of water, anything divided by itself becomes the number 1. That becomes cancel out, or 1. I'm left with moles of water, so I'm on the right track. So that means it's time to go to my calculator. And now we'll put in 37.1. I always forget once in a while. 37.1 divided by 18.0. And notice the number I get. 37.1, 3 significant figures. 18.0, 3 significant figures. I'm going to give you 3 seconds to round that off to 3 significant figures. Ooh, it rhymes. I'll give you some bonus time. All right, let's take a look. Keep the 2, keep the 0, keep the 6, my 3 significant figures. Number to round off. 1, is that 4 or less, 5 or higher? 4 or less. I drop that and the number, all the ones after that. So the correct number is 2.06. So I would get 2.06 moles of water. Let's go back and look, what did I do? First had some tea, that's what I did. But we looked at our problem. How many moles water are in 37.1 grams of water? We found out what units we're being asked to find. What do we want our answer? Moles of water. We look at what are we given? 37.1 grams of water. Now, over here, we have 37.1 grams of water. That's the only thing we can start with. What units do we want our answer in? Well, we figured that out, moles of water. Now, if we had a ratio that we could convert this to this, what goes on top of the ratio? What we're trying to get to, moles of water. What goes underneath? Grams of water. Where do I get those numbers? 1 mole of a compound equals, remember MW I use for molecular weight in grams of the compound. The molecular weight is in grams is the sum of all atomic weights, and 2 hydrogen, 1 oxygen. Three significant figures, use your atomic weights, which I will have on test number 2. Please use all atomic weights, the three significant figures. This is 101 for hydrogen, 16.0. And do the math, add it up, make sure you remember how many significant figures past the decimal when you add. You got 18.0, you put it in here. This cancels out, grams divided by grams cancels out. I'm up in moles of water, and I'm done. No, not really. I'm gonna let you try one now. Now, since you don't have your periodic table, I'll help you out. The atomic weight for hydrogen is this. The atomic weight for chlorine is this. I use these a lot, so I know them by heart. You can look at your periodic table. Ready, set, go. And let me remind you one other thing. Actually, I'll remind you two things because I would give you this. Go. Oh, it warms my heart to see everybody working on their chemistry. Thank you. If you don't have a calculator, just try and set it up. Now you know why I give more points on this, because it's more work. And when you're done, give me a thumbs up. All right, let me give you another minute and then we'll get going. So get to work. Anybody need more time? All right, let's get going because the clock is ticking. Actually, I have all digital, so they really don't, but you can imagine. All right, how do we proceed? Look at the problem. How many moles of HCl? That's what we're trying to find. What are we given? 2.110 grams of hydrochloric acid. What do? We use our good buddy, our good friend, unit analysis. And how do we do that? We only have this number to start with. And what units am I trying to get to? Well, you already figured that out up here, moles of HCl. And now it's time to use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to units wise, go on top of the ratio. Whatever I'm trying to get rid of, go underneath. Therefore, I'll put on top, nobody's yelling at me, so I assume you can see what I'm doing on the screen, moles of HCl. I'll put underneath grams of HCl. And where do I get that number? 1 mole of a compound equals its molecular weight. Oh, Dr. White's mean again. He didn't give me the molecular weight of HCl. I've got to calculate that. The molecular weight, MW, of a compound equals the sum of all atomic weights in grams. Well, HCl is 1 hydrogen, 1.01. If you look on the periodic table, 1 chlorine, 35.5, Add these up, and you get 36.51. Now, for addition, you have the same number of significant figures past the decimal as the number that has the fewest. 101 is 2 past the decimal, 35.5 is 1. Keep the 5, use the 1 to round off, 4 or less, drop it. So the molecular weight of HCl equals 36.5. And now we know from 1 mole of a compound, 1 mole of HCl equals its molecular weight, 36.5 grams. Now, before I pick up my calculator, I'm going to use unit analysis again. Notice grams of HCl divided by grams of HCl. Anything divided by itself cancels out. I'm left with moles of HCl. All right, I'm on the right track. And therefore, what do? I go to my calculator now. Let me remind you, 2.110, 4 significant figures, 36.53, 1 exact number. So multiplication, division, you get the same number of significant figures in your answer as the number you're multiplying or dividing with the lowest, in this case, 3. So let's go to our calculator. Put my numbers in, and this is the number I get. And how do you round this off to 3 significant figures? Zeros at the front are never significant. Zeros, I keep the 5, keep the 7, keep the 8. The 0 after decimal is that 4 or less? Yes, I dropped this. So the correct answer, and there are 2 ways you could write this, is 0.578. Let's go back. Over here. And one way of writing it would be 0.0578. Or if you had your calculator sent to scientific notation, you could also write this. And which answer is correct? Both. And therefore, that's how you did it. Let's go through this again. We're trying to find how many moles of HCl are 2.110 grams of HCl. And first you do is, what are you being asked to find? Moles of HCl. What are you given? The grams of HCl. Now, in test number 1, it's number 2, you'll be given 1 mole of a compound equals the molecular weight in grams of a compound. And you're also given the molecular weight, MW is shorthand for molecular weight, because Dr. White's lazy, all organic chemists are, equal the sum of atomic weights in grams. So this is what we have to start with, 2.110 grams of HCl. What units do we want to get to in our answer? We figured that out, moles of HCl. And now you use it, I got to do it one more time today, your good buddy, your good friend, unit analysis, whatever you're trying to get to, units go on top of the ratio. Whatever you're trying to get rid of, units go underneath. Where do we get a relationship between 1 mole of HCl and grams of HCl? 1 mole of a compound equals its molecular weight in grams. How do we get the molecular weight? Because you're going to have to figure that out. It's the sum of all atomic weights, 1 hydrogen, 1 chlorine, we get 36.5, put it in there, do the math, and that's how you get the number, which means 2.110 grams of HCl is a very small amount of moles. And that's how you do it. Any questions? Oh, wait, I see a chat question. All right. And Diana, don't forget, that'll be, look at the little e and the number on your calculator, because that would be times 10 to the minus 2, I think was the answer. All right, something I'm going to try today, if nobody's have any problem with it, let's not take a break. Let's do the lab and I can get you out quicker. I see some smiles on everybody's face. Don't forget, Dr. White was a student too a long time ago. And it's always nice to get out of class a little early, even though if you notice, I do give you your full amount of time and everything. I don't cheat you. All right. Oh, I see a new emoji or whatever they call them, emoji. Yay. All right. Today's lab is a super fun lab, but I'm a chemist. I like this stuff. How many of you have ever made noodles or rice or whatever, where you make a pot of boiling water and you put in some salt, sodium chloride, and it boils over a little. And if you have a gas stove, what happens? The blue flame becomes yellow. What's happening there? Now, how many of you have ever had the enjoyment of seeing the 4th of July fireworks? I hope some of you have, and you see all those things exploding in the sky with the colors. Back when I was in my late 20s, wow, that's a long time ago, a couple friends of mine and myself, we were all big guys like me, would go to downtown Chicago and by the lakefront where they had by Grant Park, we wouldn't listen to the band. Back then they had a band play, you know, the orchestra, and afterward, then they had the fireworks. Later on, they joined them. That's not good. But anyways, we'd go over there. There'd be a massive crowd, but we got good places because 4 big guys nobody messed with. But anyways, and it was beautiful. My favorite one are the exploding red that are real loud. Can you tell red's my favorite? That's not my birthstone. But anyways, what's going on there? Well, today's lab, you're going to learn. And everybody see the lab on there? And I should have changed this to, oops, 1211. But anyways, today's lab deals with moving electrons from shell to shell. When I talked about where are the electrons in different subshells and shells, I talked about atomic spectra, where if you take an element and heat it up, it gives off light that you can break into different bands of light to identify an atom. And that taught chemists about the shells and subshells. Well, it turns out when you heat an element or a cation or molecule, certain element or parts of that molecule, the electrons go to a higher shell. And when you take that heat away, the electrons fall down back to where they were. When you add energy, electrons jump to higher subshells and shells. And say that 5 times quickly. When this happens, energy is given off. And this energy is in the form of light. And because going from one shell or subshell back to where it was for a certain element or cation, we'll see, is always the same, you'll always get the same color light. And what you're going to be doing in this lab, if we're in the lab, is taking some compounds and heating them up in a Bunsen burner and seeing what color light you get. Now, if you notice, I have 2 YouTube videos for you to look at. The first one is better than the second one. And let's take a look at the first one real quick, a little of it.
We're going to do a flame test on a number of selected compounds, primarily
Everybody see the video?
group 1 and 2
Nope.
ions.
No.
And these are aqueous solutions, and we have just
Now can you see it?
inert metal loop. We're going to dip the end into the solution and put it into the flame.
Oh, is that
And
pretty?
that excitation characteristic color is like a fingerprint for an element. So we're going to look at a number, and then we're going to ask you to identify some unknowns.
This is my favorite. Oh, do it again, please.
Lithium,
Oh, she didn't. Instant replay.
lithium, so
Now, see sodium, cations, what color? Look familiar?
and the last one,
And let's do one more, copper.
most vivid of all of them,
Isn't that pretty?
my screen.
Now, what you're seeing when she put that into the Bunsen burner was the fact that, excuse me, I'm getting all choked up. I was so excited. But anyways, ooh, awful humor Thursday. But the heat from the Bunsen burner made the electrons go to a higher shell. And as soon as they moved up away from the flame, they came back down. And immediately they gave off energy, the light. And that's what you will be doing in today's lab. Actually, I gave you the data. Let's take a look at it. And does everybody see the lab again now? Thank you. Now, you're going to be doing a series of tests. In part A, you're going to be looking at molecules where I change the cation. Now, the important thing when you're doing any experiments in chemistry, I think in any science, and a lot of chemists forget about this and get in trouble. When you do an experiment, you change only one variable at a time. When you do an experiment, you change only one variable at a time. Because if you change two things, what made the difference? You don't know. And that's how I set up this lab. Now, the first one, you're going to try different cations. If you were in the lab, we'd actually do this. And the cations you're going to try are sodium chloride, potassium, copper chloride, barium, ferric chloride, and strontium chloride. Now, I'm giving you the data, what it looks like. If you were in the lab, you'd be writing this. And notice all these have the same anion, Cl minus, but the cation, Na plus, K plus, copper plus 2, and barium plus 2, ferric plus 2, strontium plus 2, those are all the cations changed. Now, what causes the color? The cations or the anions? Well, let's do part 2. And again, we're doing experiment, same sort of thing, but now we'll use these chemicals, sodium bromide, sodium chloride, sodium iodide. And notice the cation, Na plus, stays the same, but the anion changes, Br minus, Cl minus, I minus. And look at the colors. This is correct. Students, when they always do this one, come to me and say, am I doing this right, Dr. White? I have to tell them, yes, you are. Now, just to have some fun, Dr. White likes doing this. I have students do mixtures just for the fun of it of different cations. If you take sodium chloride and strontium, this is what you get. You take potassium chloride and strontium. If you take ferric chloride, and this is really pretty, with strontium chloride, you see red with sparkles. And you won't do this, but when I have students do this in the lab, I tell them, you know something, you should have some fun. Mix whatever you want together and put down your color. Now, to make this lab exciting, there's an unknown sample. And in real life, certain compounds are identified, like what the police do. One of the ways to identify is by flame ionization test. And today you'll be doing the unknown, and you would do the same thing. And here we have not one, but two unknowns. Unknown A, notice I'm being very creative with the name, and unknown B. Unknown A has white with sparkles. Unknown B is red. Now, one way of seeing electrons moving shell to shell is by adding energy. That's what you did with a Bunsen burner. When you see fireworks, the explosion part of it gives off a lot of heat and energy. And the compounds that are put in the fireworks, special ones, give the different effects, colors. My favorite is red. But anyways, there's another way of adding energy. And that's by adding very high energy electromagnetic radiation. And the one that's safe for you to use is ultraviolet light. That won't hurt you unless you put it up to your eyes, and you don't. And if you have a UV lamp, which we have in the lab, and you shine it on something, if you have certain things, it will then glow, like glow in the dark paint. And by shining more light, you add more energy. And different colors last longer. And what I did, if you were doing in the lab, I made it up myself. I have index cards with 3 stripes. I'm not telling you what color they are. And you got to put them under the lamp. And then, because we're not going to shut off the lights in the whole lab, I came up with very expensive viewing device, a brown paper bag from Jewel, which I have a bunch, and people put the card in there and then they can look. But since you're not going to do that, I gave you the data. And here, glow in the dark paste. How does it work? That's again, electrons moving shell to shell. And here, how do you add energy? By light. So what you're going to do if you were in the lab, you take the special glow in the dark index cards, and one's a stripe, another B and C, hold it under the lamp, and then you look what color, and then how long does it last? And if it's more than 3 minutes, you put greater than 3. By the way, the green would last about 15 hours. No, you're not going to stand there for 15 hours to wait. So that's why I have it here. And that's today's lab. And you'll be answering the questions at the end. And this is due next Thursday. And like I promised, I got you out a little earlier, but it's a fun lab. Definitely go back and look at the YouTube, or if you really want to have some fun, look at some fireworks on YouTube from the 4th of July. They got a bunch of good ones there. And I always like going and watching that. And with that, I'm done for today. I'll be sending out an email because I got to look up which one, what chapter we'll do for the ionic compounds problem set on Tuesday. And with that, I'm going to say bye, gehen gesund, be healthy. I'll see you on Tuesday. Don't forget, the lab that we did last week is due today by the end of the day or whatever. Please make sure you hand in the labs because that's easy points. And with that, bye, gehen gesund. Have a great weekend.